What's up, CoderByte? Welcome back to another data structures and algorithms video. I'm Elizabeth, and today we are going to be talking all about graph traversals. Today we're going to tackle breadth first search traversal. If you haven't seen our first video in this series yet, I will link it down below, where we went over all of the different kinds of implementations you might want to use when implementing a graph in JavaScript. Today, we are going to be actually coding a traversal and doing our first interview problem. So let's get started. Most graph interview problems will involve some sort of traversal, right? Because how useful is it if you just have a bunch of nodes of data and some connections between them if you can't traverse that graph and look for the different how the data is related? So there are two generally main ways you might traverse a graph. One is breadth first traversal, which we'll be talking about today, and the other is depth first traversal. Now, this might sound familiar to you if you've seen our tree videos. These are similar to those traversal methods for trees, but definitely there are some differences. So be sure to keep watching if you'd like to know more about traversing graphs. What will we cover in this video? Our learning objectives here today are to understand the breadth first traversal method. We are going to implement the breadth first traversal method, which will kind of just be how would you walk over this graph in this way. And then we're going to walk through an actual interview problem where you'll have to implement breadth first search traversal in order to solve the problem. Most interview problems that involve graphs will involve you traversing the graph in some way. Again, how useful is data if you can't actually look through it, right? Different problems, there will be different keywords that will indicate to you what kind of traversal you might want to use, but we'll get to that, of course. But there's usually also some sort of catch, right? You'll have to, let's say, not only traverse the graph, but remember the path taken, stuff like that to make it slightly more challenging than just the actual traversal method. So we'll make sure to go over a real actual interview problem as well. So take this graph, for example. This is a graph of airport data, right? And it's obviously arbitrary. I made it up. These are the airport codes, and these are just connections between the airports, right? So you can see that you guys will have to excuse me for this video. I am using this pencil thing for the first time, so, I promise to get better. So breadth first traversal really just refers to the order in which we are visiting the nodes. So in this example, let's say I start here at the Dallas-Fort Worth Airport. To broadly traverse this graph, I would first visit all of its adjacencies, right? So here it is LAX and JFK before going any deeper down into the graph. So again, breadth first search traverses broadly into the data structure. It visits a node's adjacencies before visiting any of those nodes' children. How is this done? Using the queue, of course. Now, if you haven't heard of a queue, it is simply just a data structure that is a list, and in JavaScript, we'd use an array. And the data that goes in has to be the first data out. This is the same as standing in any line at a store, of course. The first person online is the first person to get served. Using this data structure, we are able to organize the nodes to be visited in such a way that we traverse broadly instead of deeply. I'll show you how in a second. So take this graph. So for this traversal, I'll kind of just pseudocode out the algorithm, and then we'll jump right into that real implementation in a second. So this is just the queue, right? It's, again, in JavaScript, just a simple array. And let's say we're trying to go from Dallas, Fort Worth, right? We're going to broadly traverse this graph. So we would take for our first node, right, which is this Dallas Fort Worth airport, and we would enqueue it, or we'd just push it onto the queue, right? Now, this algorithm goes as follows. We take things off from the queue from the beginning, right? The first stuff in is the first stuff out. So when we go to traverse the graph, we immediately, if there's anything in the queue, we shift the first element off of the queue, and we begin to visit it, right? And what visiting it means basically is just enqueuing all of that node's children onto the queue if it's not already there. So in this case, we would enqueue its children. That is JFK, right? And then we would enqueue LAX. And then Dallas would be visited, right? So we still have some stuff in our queue. Let's go to JFK. Pop that off. Now look at all of JFK's children. Oh, Dallas Fort Worth, already visited. Don't add that on. Boston, excellent. Put that on, right? Miami, also not on. That's all of the children. Great. Now we go back here, right? LAX. So what do? Look at all of LAX's adjacencies, exactly. So that's whatever that is. I think that's supposed to be Newark. The N is missing on this. And San Francisco and Honolulu, right? And we would add that to the queue as well. And so on and so forth. So you'll see in a second when we code this exactly how we write out the algorithm. But essentially, because of how we're adding all of the adjacencies and the way we are pulling things off of this queue from the beginning, we are able to ensure the ordering of the nodes visited in this traversal. Okay, I hope you're ready to code up that breadth first traversal method with me. As you can see here, I have two different kind of boilerplate classes to keep track of our nodes in our graph. This should look familiar to you if you saw our first video all about how to implement the graph in code. This is implementing the edges list approach, where each node keeps track of all of the nodes it's connected to via a list called an edges list. If this is unfamiliar, check back in that first video. So here you can see here's our node class and here is our graph class. And these are just some of the methods that we worked on in that first video. I also went ahead and set us up with all of the airports as nodes and connected the airports to each other as per the graph in the slides. So let's get started. Breadth first traversal. So I'm just going to take that and I'm going to make a method on the graph. This seems like a graph method to me just because this is the kind of thing that you want to keep track. You're going to be looking at all of the nodes. So let's talk about this function signature. I think for right now, we'll just start with a start node and we'll traverse the entire graph, but I can show you at the end how easy it is to add in that end if you're looking for something, right? You want to traverse from one node to another node. So we talked about in the slides before we got to the actual implementation that when you're doing breadth first search, you're going to want to use a queue. And the reason you want to use that queue is because of the ordering of the traversal. You always want to be taking the adjacencies and then traversing them in the order that you've added them, right? So the queue is the ideal data structure because of its first in, first out definition. As you add the adjacencies to the queue, that is the order in which you will be pulling them off and traversing. So let's go ahead and create that queue. So let's say here's a const queue. I'm just going to make it an array. And we know that we're going to want to traverse the start node, right? We have to start somewhere. So we can initialize it with that start node in the queue. It's the first thing in the queue, right? And then, oh, there's my editor working against me. So for this traversal, I think a while loop is a great choice for the actual looping because we're going to basically loop until there's nothing left in the queue, right? So we can just loop until right? So while the queue length is greater than 0, if there's anything in the queue at all, keep traversing. And here what we want to do, let's pseudocode this out, is we want to pull the node off the queue. that we want to traverse, right? We want to visit it. And we want to add its adjacencies to the queue. And that's basically it. It's a pretty simple algorithm. You'll see what I mean when we actually write it out. So again, a queue, you have to, ensure that you're doing this correctly. Don't pop off that array because that will take it off the end. We want to use the shift method, right? So that's in JavaScript at least. So we want to say that the node we're looking at is the first thing in the queue, right? So that's the shift method. Take it off the front. Okay, so we have the node. Now, I think what we want to do is loop over its adjacencies. So we can do something like for const adjacency of node dot, I think it's edges list. And we just want to enqueue, right? Which in JavaScript will just be a push, the adjacency. And then we have our queue, right? And we can console.log that node, right? See what we get. So let's try and run this and see what happens. Oh, we are in an infinite loop, which, I had a feeling would happen, and I'm sure you did too. In a graph, there are many different connections, right? So what's happening here is we're going to JFK, and then we're going to I believe that's the Orlando airport, and then Palm Beach International, and then back to JFK. Because the adjacencies, the edges lists, overlap, right? We are re-adding the nodes that we've already visited back onto the queue because other nodes are also connected to them. So that's not great, right? We don't want to just be traversing and traversing. So how can we avoid this? I think a good way to avoid this is to just keep track of what we're visiting, right? And this is going to be a common theme in any graph problem, that you'll want to keep track of the visiting that you're doing, right? You're not just traversing the data. You want to remember, right, where you've gone, where you're going, the paths, that sort of thing. So for here, we can do something like const visited nodes equals a set. And the reason why I'm using a set here is because a set can only have unique items in them. And that is exactly what we need for this use case, right? We only want to add things to the set that we have not seen before. If we have seen them before, don't add them. And a set comes with all sorts of convenience methods, so we can just, kind of use that functionality out of the box. Similarly to how we added our start node to the queue right away, we can add the start node to the visited nodes array right away because we know that we're visiting that node. So I believe that's just visited nodes.add, right? And instead of pushing blindly to our queue, we want to first check if that node is in our visited nodes array, right? So if the visited nodes array has that adjacency in it, rather only if it doesn't have that adjacency in it, then we want to push it to the queue. Otherwise, we don't want to do anything with it, right? And I believe I can leave that console.log there. And if the other thing we'll want to do is add to the visited nodes, right? So after we push it to the queue, we will definitely want to say that we've visited it. So we can add that. And I believe that should be all we need to do. Let's see. Yep. So let's go over this quickly. So we start with Dallas-Fort Worth. That's great. We go to its adjacencies, which are LAX and JFK. That looks good. Then we begin to go into LAX's adjacencies, which are Honolulu, Newark, and San Francisco. And remember, LAX also has Dallas-Fort Worth as an adjacency, but it's in our visited nodes array already, so we're not looking at that again. Then we go to Boston, which is one of JFK's adjacencies, Miami, and finally Orlando and Palm Beach International, which are all Miami's adjacencies. As I said, it is pretty easy to add an end node if you are doing a breadth first search. You're looking for something, right? You're going from one node to another. So we can code that up real quick. So essentially what we want to do is pass in both a start and an end node, right? Because not only are we starting at a node, but we are looking for something. And it is pretty easy while you are in this while loop, instead of just blindly adding all of a node's adjacencies to the queue. Before you do that, I think all we can do is check, is the node that we're at the end node, right? So if the node that we're at, let's say the node.value, is the end node.value, right? We can just, let's say console.log found it and return, right? That would be it. So let's just make sure that that works. Can't read property value of undefined. That makes sense. I am not passing in anything yet. So let's say we want to go to the Miami airport. Let's see what happens. So we go first to Dallas, then we go to all of Dallas's adjacencies, LAX and JFK. Then we go to Honolulu, Newark, and San Francisco. These are all of LAX's adjacencies. Finally, we go to Boston and then Miami. And at that point, we stop. We found it. As always, it's important to consider the time complexity and space complexity of any algorithm. So when we're talking about breadth first search, generally, we can expect the time complexity to be a big O of V plus E, where V is the number of vertices and E is the number of edges. I can demonstrate this for you if you imagine that queue for a second, right? So the algorithm will grow, right? Let's say we're starting at the Dallas-Fort Worth airport. Let's add that to our queue, right? Then we add every single adjacency of that first node visited, and so on and so forth. And with each iteration of that while loop, you are iterating through for every vertex, and then you iterate once more for every edge of that vertex. That's how we get that big O of V plus E. If you can imagine when you are, this of course depends on how you're storing the adjacencies, but in general, the queue will grow with each by the amount of adjacencies for every vertex. And the space complexity is just big O of V, right? Where V is the number of vertices. That queue will always only ever get as big as the number of vertices in that graph. Remember, we're keeping track of the nodes that are already visited, so we only visit each node once. That's how that data structure grows in that linear way. Breadth first search is an excellent choice for any interview problem where they're asking to find the shortest path between two nodes. The answer being obviously that because you go through the nodes in this, the first nodes you go through are the nodes closest to the starting vertex, and you move outwards in a broad way. If there were a shorter path, you would have already found it in a previous iteration. This can kind of be visualized, let's say in this example, going from the Dallas-Fort Worth airport to the Mexico airport. You can kind of see the graph grow as our queue grows, right? So we're going from Dallas all the way to here, right? So first we add the Dallas-Fort Worth airport to our queue. And as you can see here, we can imagine that this is the first thing visited, right? And as we add our other airports to this queue, right? First comes JFK, then comes LAX. And again, it doesn't matter what order the actual nodes are added in the adjacency list, as long as they are all added in the same step. meaning you can put LAX before JFK or JFK before LAX, that doesn't matter. As the queue grows, you can imagine kind of another intermediary data structure forming, which looks like a tree, where each level of the tree signifies how far away those nodes are from that first starting node. So we can see that as we add the adjacencies of all of the children nodes, we begin to have this leveled graph. So here would be, right, Honolulu and Newark and San Francisco, let's say. Boston, Miami, etc. As promised, it's time for that interview problem. Given a graph of users and their connections, find the smallest distance between two users. Okay, so let's talk a little bit about how we might immediately be able to tell that the breadth first search algorithm is one that we want to use. So this is a dead giveaway, right? Anytime anyone asks you to find the smallest distance between two users, or between two nodes, excuse me, you'll likely want to use the breadth first search algorithm. Again, because of that kind of excellently laid out way of the data, that you're always looking for all of the nodes closest to the starting node before you get to any of the nodes farther away from the starting node, right? So in this example, there are a few differences to the actual solution to this versus just the plain breadth first search. The first being that we're going to have to keep track of the actual paths, right? So far, we've only traversed graphs. In this example, we're going to have to maintain some sort of, we're going to have to remember, okay, so I'm traversing this node at this moment. How did I get here? Where did I come from? Where am I going? That sort of thing. So let's jump right in. So once again, we are back with our boilerplate node and graph classes, and we are going to try and answer this interview problem. So the differences between a regular traversal and this interview problem are mainly in that we want to keep track of those paths, right? We're asking what is the path from point A to point B, and how is it the shortest, right? So right away, because they're asking for the shortest path, I think breadth first search is the way to go, right? So let's begin by writing out some of our breadth first search that we've already learned how to kind of, write the bones for. So let's say the breadth first traversal, we're going to get a start and an end, right? And we can immediately make a queue, put that start node in there, right? That will be the same for anything you're doing any traversals with. And we can make that while loop again, right? That's going to be pretty standard for any of these graph traversals. So, okay, so we pull our first node off of that queue from the beginning. So let's shift that off of the queue. And essentially what we want to be doing is, right, we want to add its neighbors to the queue. And we also want to somehow track where we're coming from, right? Where are these nodes that we're adding? Where are they coming from? Because that will help us answer the question of what was our path? How did we get from start to end? Comment below if you can't spell adjacency to save your life or to get a job. And we will want to push each of those adjacencies to the queue, right? And we can, of course, also log out the adjacency dot value if we want to be looking at what we're doing as we code. Now that will take care of pushing all of the adjacencies onto the queue. We still have that problem of visiting queues multiple times, right? So what we can do is we can add that tracker, that visited nodes tracker. Now, I think I'm going to use an object here because in this example, I think that what we can do for keeping track of the visited nodes is use it to remember the path from which they came, right? So our queue is, you can think of our queue as the data structure responsible for dictating where we go in the traversal, while the visited nodes object can keep track of where we've been. In our previous example, we used a set, right? Because we just wanted to make sure we weren't visiting nodes multiple times. Here, we can keep track of where a node, who a node's parent was, and use that to reconstruct our path afterwards. So I'll show you how we do that in a second. But initially, we want to add the start node to the visited nodes object, right? So we can go ahead and do that at the beginning. And I'm going to use the start node.value just because this is an object now, not a set. And I'm going to set this equal to null, and you'll see why in a moment. So back in our while loop, we're here, right? We want to make sure that we only want to add things to the queue if the node is not already in the visited nodes list. So we can do something like visited nodes.has own property, the adjacency.value, right? If it doesn't have that, because as you can see, if we just checked for whether it was there, we'd have that, it would be a false negative because we've set it equal to null. So we check if it has that property. And only if it doesn't have that property do we want to add it to the queue, right? So what do we do? What are we storing there, right? In our other example, we were just adding to the set. Here, in this loop right here, we have access to node, which is the adjacency's parent, right? And it's all of its adjacencies. So this is the opportunity for us to capture where is that adjacency coming from? Who put it on the queue, so to speak? So when we add it to visited nodes, instead of just adding it to the set like we did in the previous example, we can actually set at that adjacency in the visited nodes object, we can set its value to be the node that added it, right? So let's walk through an example. So that means that if we get to the max node, right, we're getting to the max node. Max is an adjacency when the parent, Hannah, is being visited. So all of Hannah's adjacencies will have Hannah as its reference, its parent, in this visited node object. So what we end up with will be a structure that kind of every single adjacency has a pointer back to what it was adjacent to when we were traversing the graph. So we can log this out just to be a little bit clearer. So let's do it at the very end of the traversal. So here you can see we have our visited nodes object where Hannah, where we start, has a parent of null, Max has a parent of Hannah, Mel has a parent of Hannah, Mary has a parent of Hannah, Nis has a parent of Hannah, Liz has a parent of Hannah, Dan has a parent of Nis, right? So that's because when we start to traverse the graph and we get to Dan, Dan's parent in that traversal was Nis. Now, Nis's parent was Hannah. So I hope it's becoming a little bit clearer to you how we can use this structure to reconstruct a path of how we got from point A to point B. Okay, so the only thing that's left at this point is to actually reconstruct that path, right? So at that point, so we'll do that here, right? After we take that node off, we can check if that node value is equal to the end value that we're looking for, right? We can, let's say, console log that we found it. And we can return this dot reconstruct path. And then we'll pass in that visited nodes, the start and the end. Excellent. So now let's code this out. This is the reconstruct path. We get the visited nodes, the start node, and the end node. And essentially what we want to do is we want to start from the end of the path and work backwards, right? Because this is like it's similar to a linked list. The last node has access to its previous node, and we want to kind of loop backwards in order to reconstruct this path. So what we can do is we can, initialize this occur node, right? To keep track of where we are, and let's set it to be the end node. And another while loop will do, while the cur node is not null, which this will of course stop when we get to that initial start node that has a value of null in our visited nodes, right? That was how this is kind of our like breaking, we're at the bottom. So that's why we're looking for that, while the current node isn't null. We basically want to create a path, right? We want the nodes in the order in which we traversed. So we can keep track of this in a, shortest path array, right? That's what we're looking for after all. And essentially, right, this is going to be, we're going to want to push that current node into the path. So now we have our end node, right? We've started our path. We have the end node as our first, place in the graph that we've traversed. And what we can do is, let's take a look at this visited nodes array, right? So we start with our last node, right? In this case, we've traversed the entire thing, but let's say we start with Nicolette, right? So the next node that we want to look at, right, is going to be, if Nicolette's parent was Chris, then we want to see what was Chris's parent, right? We want to know, how did we get there? So the way we can do that is, it's pretty simple. We take the visited nodes, right, at the current node's value, and we make that our next current node, right? And in that way, we push the loop forward, or backwards, if you will, right? Because we're looping through this in a backwards manner. We start at the end and we traverse backwards to recreate this path. At the end of this, of course, we will have, let's see, console.log the shortest path. Let's see what we get here. So we get Mabel, Liz, and Hannah, which is great. That's exactly what we wanted, right? Except it's backwards, of course, because what we're doing is we are actually looping through these visited nodes, and we started at the end and then we go to the beginning. So before we return, let's return the shortest path dot reverse, and we should be good to go, right? So to recap, today we talked all about breadth first search. We talked about graphs and how any problem that's asking for the shortest path is likely going to be a good application of the breadth first search algorithm. We talked about using a queue as a method of storing the nodes in the correct order in which we'd like to traverse them in, which is broadly as opposed to deeply. We also did our first interview problem together. We traversed a graph of users and found the shortest path between two users. I hope you enjoyed this week's video. Next week, we're going to be talking all about depth first search traversal and doing some more awesome interview problems. Have a great week, team.